Very happy to introduce today's colloquium speaker, Phillips from the Department of Physics at the University of Illinois at Urbana-Champaign. So everybody who introduces Philip always emphasizes the doubleness of things. Like, born in Trinidad and Tobago, his name, of course, his middle initial is W. So they moved to Walla Walla when he was young. He went to college in Walla Walla. Yeah, it's okay. I'm done with that now. Philip was a Miller Fellow at Berkeley, and when he took his first faculty position at MIT, he was a chemist, and he got interested in strongly correlated electrons in conjugated polymers, and that led him down the dark road to physics. And so he moved from MIT to Urbana in the 1990s of strongly coupled electron systems, many body systems. And this includes weird effects like mottness. Again, two P's, double, since we had to keep doing that bell. Which is the strange state that strongly coupled electrons can have in high-temperature superconductors, for example. And so Philip has a theory for that. When the iron-based nuclide superconductors hit, Philip got into that and made major contributions. Now the topological topological insulators and all of their interesting states are the thing to explain. Philip is in the forefront of that too. Although today, I think what he's going to tell us about is something a little bit different. It's a new idea he calls Unparticles that I think has gotten him into conversations with folks in CCPP, and it's going to be an interesting connection between solid-state physics, cosmology, and things that go twice.
Thank you, David. It's great being back in New York at NYU. I haven't seen David since the last time I was here. We normally run into one another at March meetings, but I think we both quit going to March meetings at the same time. So I'm going to talk about unparticles in high-temperature superconductors. I want to convince you of one thing, and you'll see what that is. My partners in crime are three students, Brandon Langley, Garrett Vanacore, and Kritsangapong Limtragul. I guess only Garrett is smiling. Okay, I don't know why. Okay, so let's just start at the very beginning, and I'll get to my point. Superconductivity is a very old phenomenon. And here is the original data that was taken in this man's lab, not by him, but by his assistant, and only he shared the Nobel Prize. And superconductivity has any number of extremely weird properties. The key weird property is the Meissner effect. And the Meissner effect was first explained phenomenologically. And the key phenomenological statement was a statement about the behavior of the current in the superconducting state. That namely, J scales with A, and from that simple relationship, one is able to deduce that the field inside a superconductor decays exponentially. Now, the new problem is explaining high-temperature superconductors. And there are any number of theories of the superconducting state. But the serious problem is explaining the strange metal, what these systems are doing before they superconduct. And that's what my focus is going to be on. I don't particularly care about the superconducting state. And I think ultimately most people don't. It's really what's going on before, because that represents a serious departure from the standard theory of metals. Now, my key point today is that explaining the strange metal also requires, and hence high temperature superconductivity requires, another statement about the current. I'm going to convince you that the current has to have an anomalous dimension, and this anomalous dimension is not d minus 1, as it typically has to be. In fact, is fractional. So this is a very weird statement. Okay, so what is the strange metal? So before I get onto the strange metal, let me just talk about what we expect in a typical metal. So a typical metal, electrons are bouncing around, knocking off of the ions, and the conductivity is not equal to infinity because there's momentum relaxation. The statement of momentum relaxation is that there's a part on the right-hand side of the equation that represents the exponential fall-off of the momentum. So this is just the Maxwell part, and then this is the phenomenological momentum relaxation. And that leads to a conductivity of the Drude form, and tau is now the rate at which momentum is relaxed. And you set tau going to 0, you end up with this infinite delta function peak at omega equals 0, as is typical of a perfect conductor. Another thing about the standard theory of metals is the F-sum rule. The effective number of charge carriers, in other words, the stuff that's coupled to the electromagnetic gauge, you can obtain by just summing the optical conductivity over all frequencies. Typically, all you need to do is integrate over the band that the charge carriers are in. So there can be a cutoff here. So those are the two facts about metals that I want you to keep in mind. And that's all you need to know. Okay, so here's a strange metal. So this data these data were taken in 1990 at Bell Laboratories. And notice the title of the paper, Growth of the Optical Conductivity in the Copper-Oxide Planes. And so what do you see? X equals 0, you see that the optical conductivity crashes to 0 and it remains 0. This is just some noise. So this is the gap in the system. So that's already different from the... X is the number of charge carriers that you introduce into the system. So X equals 0, the system is an insulator. As you dope the system, so doping is just the number of X's that you have in the system. As you dope it, this optical conductivity, which extends to all frequencies, this part goes down and this part grows up. So there's a mixing between the stuff at high energies and the stuff at low energies. And it's this mixing that is indicative of the strange metal. And it's what gives it its strange behavior. And it's explaining this that is my principal focus today. So first thing, what is a Mott insulator? So Mott was interested in the state of nickel oxide. And nickel oxide has it's supposed to be, so it has a partially filled band. And the thing we learned about in any solid state course or just even high school chemistry is that things which have partially filled bands tend to conduct electricity. That's not the case here in nickel oxide, which needs 2 more electrons to fill the band, in fact is an insulator. Now what Mott said is that perhaps it costs a certain amount of energy, so I've just illustrated this with 1 electron per site. Perhaps it costs a certain amount of energy when 2 electrons tend to occupy the same place. So what Mott said, his picture of a Mott insulator is exactly this. It costs a certain amount of energy. I'll let U be that energy. If you're in a regime where U is much bigger than this hopping matrix element, it's not advantageous for the system to delocalize. The ground state actually is electrons being stuck in various places. And if that's the case, the density of states, the single particle density of states, will develop a gap. So this is a gap without changing the size of the Brillouin zone. There are theories of Mott insulation which eliminate the Mott problem. Namely, that you just change the size of the Brillouin zone so that there are no empty places for the electrons to go. I will ignore that because that has nothing to do with the problem.
What are the axes on that graph that you're showing?
The important thing is that there's nothing here.
I'm sorry.
Energy versus...
Okay, so this is the density of states. So it's the number of states per unit energy. Okay, and I just drew this to show the fact that at mu equals 0, there's nothing. Okay, so there's a gap. And this gap has nothing to do with symmetry breaking. It's due entirely to the fact that the interactions dominate. So that's the statement of Mott. Now let's look at the doping dependence of a Mott insulator. As we change the number of dopants, what is new about a Mott insulator? Okay, so we need a modified sum rule. Since there's nothing up to the optical gap, all the charges that we introduce should be present at states below the optical gap. So the number of charge carriers, the stuff that's coupling to the electromagnetic gauge, if we simply do this now sum rule, we should get the total number of charges in the system. Okay, now if we start with the band that is, it just goes up to a certain point and we deplete it, we should just get n effectives proportional to x. So in this system, we start off with a half-filled band. X is the number of carriers we remove from the system, and hence the number of effective charge carriers should just be the weight of the empty band. Here's what you see in the copper-oxide superconductors. That the total number of effective charge carriers in the system is in fact bigger than x. It's this line right here. So this is when you introduce holes into the system or electrons as the dopants. This would be if n effective were equal to x. Clearly seen is this thing is always bigger than x. Okay, so this is something that's weird. In a metal or a semiconductor,
You got from integrating the
right,
sigma
of omega. And you know the volume of the unit cell, you know everything on the right-hand side. It's a straightforward integration. And this has been known since 1990. And it was published by people at Bell who never make mistakes. So, except in one case, which we will not talk about. Okay, so there's no reason. This in fact is known. Okay, so one of the questions I want to ask you is, this is really weird. The stuff that's coupling to the electromagnetic gauge is bigger than the amount of dopants you put into the system. And it's happening from very small values of x. So one thing I want to ask you is, what is the low energy model that gives you n effective bigger than x? And the answer to that question might surprise you. So this means that they're excess charge carriers. And these charge carriers are not related to the dopants. And there were no charge carriers beforehand. Now, everything you put in can be given a particle interpretation, which means this excess stuff has no particle content. Okay, to understand that statement, let me just show you that this comes about by counting charges that you put into a Mott insulator. Okay, so here's a Mott insulator. I have 1 electron per site. I could put 2, but the system is insulating at this point. And what I want to do is work in the limit in which I can't have double occupancy on any site. Okay, in that limit, I can ask 2 questions. How many ways are there of doing a photo emission experiment? So the photo emission spectroscopy, I knock an electron out. How many ways are there of knocking an electron out? Well, there are n electrons, hence there are n possible ways of doing that. How many ways can I do an inverse photo emission experiment? I'm adding an electron to the system. There are n ways of putting electrons on n sites. Okay, so there are n ways of doing that. All of these lie at an energy value U above this. Now I want to ask the question, if I in fact introduce an empty site into the system, how do these weights change? Now normally if you have a semiconductor and you remove an electron or a non-interacting system, nothing will change about the band above the chemical potential. You'll just knock the number of states you have out of this system equal to the number of dopants that you put into the system. But I want to show you that that's not the case here. Because what you mean by high and low energy is actually cannot be answered independently. Okay, so the number of ways of removing an electron from the system, since you only have n minus 1 electrons, is n minus 1. And the number of ways of doing an inverse photoemission experiment, so you constant energy U, has also gone down by n minus 1, because there are only n minus 1 ways of getting double occupancy. So this has changed, that has changed, but you have to conserve the spectral weight. Because you have 2n states, you have 2n minus 2. And it's because this empty site, you can put an electron on that site with either spin up or spin down, which means the spectral weight of that site is actually 2. So if I have x dopants, the answer is just 2x, and I've divided by n. So the actual weight of this lower band is 1 minus x plus 2x. So no, it's not x, it's 2, and it's because one state is transferred above and one state is transferred down. So this is the counting of the number of states that give rise to a static change in the spectral weight at low energies. Okay, now I want to relax the constraint of 1 electron per site and let the electrons do whatever they want to do. Now remember, when I don't have U equals infinity, I can have double occupancy. And when you see a blue and a red site together, blue and red together, that's double occupancy. I start off with one empty site. And as you see, I now have more than one empty site. And every time I have an empty site, that is changing the total spectral weight at low energies. I have more empty sites, hence I have more low energy degrees of freedom. Hence the total number of low energy degrees of freedom I have in the system is in fact bigger than 1 plus x. Okay, now why is this a problem? And this in fact has been known since 1967. And in fact, the person who did this was A.B. Harris. And most of you know him for the Harris criterion. After he did this work, he left strongly correlated electrons because this is a particularly weird result for the following reason. Okay, why is this a problem? What I want to do is just count the number of electrons that I can have at low energy or at high energy in the system. And that's independent of the Hamiltonian. It's really just determined by the number of sites that you have. Okay, so I just want to count electron states. Okay, so I'm going to let x equal n sub h minus over n. And the number of ways of removing an electron in this renormalized unit is just 1 minus x. The number of ways of adding an electron, so it puts you into the high energy states, is 1 plus x. The number of addition states, including this one, is in fact 1 plus x. But not all of these addition states lie at high energy. The ones that go here lie at low energy. So in fact, it's 1 minus x plus 2x, which equals 1 plus x. So the total number of ways electrons can be put into the system at low energies is 1 plus x. But remember, the total spectral weight at low energies is in fact bigger than 1 plus x, which means there are more charge degrees of freedom at low energies than there are ways of putting electrons into the system. Which means some of these degrees of freedom at low energies have nothing to do with electrons. Okay, and that in fact was known since 1967. It wasn't quite understood this way, but that's what it means. And so what this means is that a UV complete theory has nothing to do with what's actually coupling to the electromagnetic gauge. Okay, so what's the extra stuff? Okay, so let me ask the question, what else is weird about the cuprates? What else is weird about the optical conductivity? Well, here's the other thing that's weird. There's this regime, so this is the optical conductivity again, and it obeys this Drude formula, so there has to be some relaxation mechanism. But in this regime in frequency between, I'm losing my pointer. Oh, excellent, you have a green one as well. Okay, good. So there's a regime in frequency where the optical conductivity scales to this minus 2/3 power. And this is a very weird sort of result, and this field has been puzzling over this since this has been seen. It was seen earlier than this experiment, but this one illustrates it very clearly. And as you see, this scaling regime is independent of temperature. Okay, and it's also been seen in these YBCO films, so it has nothing to do with particular atomic structure of the other cuprate. Okay, now we know one thing. If you have some sort of criticality, that gives rise to scale invariance, that gives rise to power laws. Now what we'd like to do is reverse this argument. That if you see power laws, it implies scale invariance or some sort of criticality. Okay, now that was the first argument made. Okay, and that argument was made by none other than Phil Anderson. Okay, so Phil Anderson said, we're seeing this power law in the cuprates. It has to be due to some sort of scale invariant stuff. Let me just use the only scale invariant propagator that I know about for electrons, and that would be the propagator for one-dimensional electrons, and it looks something like this. Notice omega and k have the same scaling. This is just some fractional power, and hence it's a propagator that has fractional scaling dimensions. Okay. But it's only valid for a 1 + 1 dimensional system. Okay, so Phil computed the conductivity, and he argued that you should not include vertex corrections because that's just not what you're supposed to do. Okay, and he says, in fact, the conventional theory of transport is not applicable because the conventional theory of transport will not give you this result. Okay, and with this exponent, you can get anything you want. Okay, fine. So if in fact you were to go include the vertex corrections, you would not get this fractional power because you're limited by Ohm's law in a gauge invariant calculation to get no other exponent than other 2 - d. Okay? So the other problem is that the cuprates are in fact 2 + 1. So between 1997 and until 2012, there was no progress on this problem. And in 2012, what happened was there was a calculation done by string theorists. And let me just show you what that calculation told us. That calculation was done by Horowitz, Santos, and Tong at Santa Barbara. And over a fairly wide range, the claim is that you obtain this omega to the -2/3. So there was big excitement. String theorists have solved the strange metal problem of the cuprates. I'll tell you exactly what a gravitational lattice is. Okay. So this is in fact a remarkable claim. If in fact you're seeing this, the thing I've not shown you is that it also, the conductivities of the Drude form, which means that you have to have there's some sort of momentum relaxation present in this system. Okay, so could string theory be the answer to this problem? Okay, let me just back up a little and tell you the particular part of string theory which is being used here. So I've already told you that in strongly correlated systems, there's a disconnect between the UV complete theory and what might be going on at low energies. The degrees of freedom are fundamentally different, and a clear example is QCD. Okay, so how do you go from UV to IR? Well, in some cases you can do it, but in most cases it's very difficult. In condensed matter, a typical expansion parameter is 1 over your ego, which for some people is actually 0. And, but really what you're supposed to go from UV to IR is you're supposed to compute the beta function. Okay, and this is something which is local in energy, and that tells you how these identical copies of the system, all at different energy scales, or different values of the coupling constant, which is a function of energy, are related to one another. Now, because this is a local transformation, one should be able to geometrize this whole picture. And that is the essential claim in the mapping of strongly coupled theories which live at the boundary to a problem in gravity. Now this doesn't work for any, so the whole content of gravity, since there's diffeomorphism invariance, is in fact some non-local thing. So the kinds of geometries for which this statement is true are ones in which there is a particular value of the beta function, namely 0. So you're at the scale invariant point. So if you simply append to the standard Minkowski dimensions an extra dimension, which has to do with the running of this energy scale, and demand that you have scale invariance as a scale invariant transformation, solve the Einstein equations, the metric that you end up with is just anti-de Sitter space. So the conclusion is that we've replaced this strongly coupled system, which lives at the boundary. This is the coupling constant. This is just the curvature of this space-time. You've replaced this with a geometrical problem. And the claim then is that you can in fact have fundamentally different symmetries at the boundary as opposed to the bulk of the system here. So in other words, what is really happening is you've replaced the renormalization procedure with general relativity. And some write this equality Rg equals Gr as the commutator of R and G is equal to 0. Which is in fact my favorite equation because it really is a profound result. That both of these statements about strongly coupled systems and general relativity all really rely on sort of non-locality, and the fact that both of them are essentially telling us the same thing is quite profound. Okay, so ultimately then the underlying theory has to be cannot be a system at 0 coupling constant. So the statement from the ADS from the gauge gravity picture is that certain strongly coupled theories have gravity duals. So the quantum theory lives on the boundary, and in this inside in the bulk of the system one has gravity. Okay, so the equation which has come out of the Horowitz work is this one right here. You solve the Einstein-Maxwell equations, and you put in details about enough to give you some mechanism for momentum relaxation, and you'll end up with omega to the minus 2/3. Now, these details that you put in aren't very tethered to anything. So really, it's Einstein-Maxwell plus a non-uniform charge density gives you the physics of the Cuprates. And that's why this was such an amazing claim, because there were no tuning parameters in this or this. Okay, so another group did these calculations, Donos and Gauntlett, and they in fact did see this Juda conductivity, so the real and imaginary parts are related in this way. But then they said if something goes as a power, rather than extracting that from a log-log plot, let's go and plot this function. Okay, so if the conductivity is going as a power, then that power, which is minus 2/3, should be equal to this function. So you take the second derivative over the first derivative, multiply by omega, add 1, that should be the power. So what you're looking for now is if you were to plot this function here on this axis as a function of this axis frequency, do you get a constant? Okay, and as you can see, they did not get a constant. They got something which oscillates fairly wildly. And for any range of parameters that they looked at, they did not get a constant. Okay. Now, so the other people did not do this. They simply did a log-log plot. Okay. So the question I want to ask is who is correct? Now, in solid state, we prove things vigorously. My impression from high energy is that they prove things fairly rigorously. So we have to go and redo the calculation. Okay, so we had to go and learn how to do these calculations. No one was really settling this debate, so we learned how to do all these calculations. They're fairly intensive. So the model that you use is you have some gravity part, some E and M part, and some lattice. So the gravity part looks fairly standard. And then...
Just to be oriented, when you're talking about gravity, it's some sort of effective theory that's like gravity. And the real, I mean, it's not literally gravity in this room.
Yeah, it's real gravity. It's a metric. It's sourcing a...
No, but I meant the coupling constant and all of that.
Gn is Newton's... Yeah, I mean, in front of this action...
So if you did it in a
Yeah.
space station without gravity.
Look, Gn is Newton's constant, okay?
I understand, but I'm wondering, asking if, in terms of the application to the Cuprates, are you predicting that you would get a totally different answer if you did these experiments in the space station?
Okay, I'm not saying that, I'm saying that so I'm making a statement about what is the effective theory underlying a strongly correlated system. Okay, so that's my statement.
And so you're using it as an analogy, maybe?
No, I mean, those who take ADS CFT seriously, we really think that it's not just an analogy, that's just the way the world is.
Sure, that it can be applied in many different theories. So I'm just wondering, are you saying that in the material, there's an effective field that's like this system that people...
Okay, so what I'm saying is this. We understand field theories only because there's a renormalization principle. That's really how we understand field theory.
You're right, but that you don't need Newton's constant.
Okay, so as long as field theories we understand them because of the renormalization principle. A field theory then is characterized by an extra dimension in which you are now evaluating the system at various values of the coupling constant. That maps directly onto a gravitational system. That's the claim. Okay, so we're trying to understand a low energy model of the Cuprates. Well, that's just what you have. Okay, now I haven't proven this yet, okay, but the application of this to the Cuprates would suggest that something like this would be true if the work of Horowitz, Santos, and Tong is correct. So their calculation so far is just, the Ricci tensor. This is the cosmological constant, and this is just the field strength. So this part is just Einstein-Maxwell. And the only thing they added to this is just a scalar field with some with some potential, and I'll tell you the details of this. So they solved this system, and so as long as you have a field strength, and you have and this is a finite chemical potential, it's sourcing a charge density at the boundary. That's all you need to be able to do linear response, to calculate a conductivity. Okay? So, so you have a metric, you have a potential with a scalar field, and you have a gauge field. Okay? And your space-time is something that is asymptotically anti-de Sitter. And this... Let me just stop here, enough details on this. Okay, so the key thing is that this potential is giving rise to some non-trivial charge density profile at the boundary. And to do any sort of calculation of the conductivity, you need to perturb with an electric field. So you perturb with an electric field. And then that will lead to time dependence in all of your basic fields in your system. You can calculate the conductivity. You have these 8 coupled differential equations which you have to solve in this curved background. And this is what my student learned how to do. And you have to solve these without making any mistakes and put in gauge invariance and all of this. So let's assume all of this can be done. Okay? What do the results look like? Okay, now, before I get to that, when you actually, if you just write down the equations of motion for the fluctuations, what you find is that there is a term which looks like this. So it's as if the graviton actually has a mass, and this mass is proportional to the potential. Okay, so underlying these gravitational constructions is actually a mechanism for momentum relaxation. And this gives rise to the fact that the stress energy tensor is actually not conserved. This component of it is not conserved. And that's why you get a Drude conductivity in these gravitational crystals. Okay, now it turns out that there are some differences between Donos and Gauntlett and what Horowitz, Santos, and Tong did. Okay, so they used a potential which is just a cosine kx, so they're only broken translational symmetry along one direction. And Donos and Gauntlett added an extra symmetry into the problem, such that if you add this into the Lagrangian, it has no effect, except for this phi of z factor. So this will affect the equations of motion along the z direction, but it will not give you anything else. Actually, it will affect the Minkowski directions because there are derivatives with respect to x and y, and you'll pick up a factor of k. But other than that, so what they've really done is disconnected breaking of translational symmetry with a charge density that is inhomogeneous. And before it was thought that both of them had to go together, and they don't have to go together. Okay, so what we did is we said, okay, let's choose a potential that will interpolate between these two different results. So if you have theta equals 0, you get Horowitz, Santos, and Tong. Theta equals pi over 2, you get Donos and Gauntlett.
Is x 5-dimensional or 9-dimensional?
It's
the field theory coordinate, or?
That's just one. It's x, y at the boundary, and t, and the bulk is now 3 plus 1.
Okay, so the bulk coordinate.
Right. So at the boundary, so z is the bulk coordinate. Okay. So the boundary is just x and y. I've only broken translational symmetry along one direction on the boundary. Okay. Okay. Okay, so here are some of the parameters which go into this, and you see that in fact for theta equals pi over 2, the calculation of Donos and Gauntlett, this is completely featureless. It's certainly very non-zero for the other case. And this translates into the fact that the charge density in Donos and Gauntlett is completely flat. So they have a completely featureless charge density at the boundary. The other case is this one. So an easy out for Horowitz, Santos, and Tong is simply they didn't do the right calculation. To actually get this omega to the minus 2/3, you need to have a non-trivial density profile at the boundary, something that looks like this, something that's oscillatory, that breaks the translational symmetry in the charge density. Okay, now with our model, we can determine which one of these conditions is actually necessary. Okay, so we went and redid the calculations, and here are the conductivities, the real and the imaginary parts. They do obey this Drude form. These are just different values here. But the important thing that you want to know is there a power law? And, okay, this is theta equals pi over 2, theta equals 0, pi over 2, this theta equals 0. As you vary theta, the results don't change very much at all. So whether or not the boundary has a charge density that's inhomogeneous is completely irrelevant. The only relevant thing is the fact that you've broken the diffeomorphism invariance, and hence you have a mechanism for momentum relaxation. That's the key point. And all of these conductivities look essentially the same. But none of them give you a power law. Okay, now there's one last thing that we can try, and here is the phase relationship between the real and the imaginary parts. It's not equal to 60 degrees. We can also change the relative amplitude of one of these cosine fields relative to the other. No amount of fiddling will give you this thing to be flat. Okay. Now, I've spoken about this at several string conferences. I think everyone is convinced that now that this is the right result. Any calculation which has a massive graviton at this level cannot give you omega to the minus 2/3.
Can I ask something? So it's clearly not flat, but I mean, how does the experimental data for this omega
Okay, so the experimental data seems to go from about 1,000 to 10,000 wave numbers. So 0.1 to about 1 eV. So it's at least a factor of 10.
It looks consistent with flat.
It looks completely consistent with flat.
Like if you plotted that in the same way, where I'm not sure why.
Right. So if I go and plot the experimental data with the same level of care, I would get a completely flat line.
The error bars would be much smaller than those oscillations.
Yeah. Well, the error bars we would be introducing because we would be having to take a numerical derivative of the data, which, okay, and you know what, yeah, that's right. Okay, so the key thing right now is that these gravity constructions at this level cannot explain the Cuprates. Okay, so solid-state physicists might breathe a sigh of relief, but don't do that yet, okay? Okay, now what is the intersection between what Anderson did and these ADS groups? Okay, a key feature of both of these is scale invariance. That's the only part I'm going to focus on right now. So both of them have scale invariance. Okay? And so what is scale invariance? Well, it just means you have some sort of invariance over all length scales. Okay, and I'm going to assume that if you're seeing power laws, it's telling you that some sector is scale invariant. It's our only way of understanding these non-trivial power laws. So that's an assumption. If you have some other way of getting that, that's fine, but I don't. Okay, so I want to ask the question, how can you explain these power laws with the stuff that we traditionally use? Okay, for example, particles. Okay, so what are properties that particles share? Well, they have a U1 type symmetry. So particles have charge and mass, but charge and mass are very different. Okay? Because there's a conservation law associated with this, but over here it's very different. Okay? So mass always sets a scale. Charge doesn't really set a scale, but so if in fact we're seeing stuff that is scale invariant, it cannot have a well-defined mass. Okay, so I need to search for stuff that does not have a well-defined mass. Okay, so what stuff doesn't have a well-defined mass? Well, mass is energy. So ultimately what I'm trying to do is explain stuff that doesn't represent any kind of coherent excitation. Okay, so what has an ill-defined mass? Okay, so let's just look at a Lagrangian which has a well-defined mass. Okay, and this Lagrangian, as you well know, breaks scale invariance. Okay, if I simply scale x in this way and the field does not scale, I find that there is no amount of scaling of this and that term such that the Lagrangian is scale invariant. So this breaks scale invariance. Okay, now, but there's something that I can do. Let me solve the equations of motion at each value of the mass. So now let's introduce another coordinate here. And let me represent my Lagrangian as an integral over all mass. Okay, so I'm integrating over all mass. This theory is in fact scale invariant. If I just do this change now, any change I introduce here into the mass, I can just absorb into changing my variable of integration. And scale invariance is restored. This doesn't describe particles. In fact, this describes unparticles. Unparticles are stuff that has no particular mass. In fact, they have all possible mass. So it's not that they have zero mass, they have all possible mass. Okay, and the propagator here is just something that looks like whatever the distribution of mass is over the standard mass of propagator, and this will give rise to a standard kind of power law. Okay, now, so one can think about unparticles as from the continuous mass formalism as a bunch of scalar or vector fields with some Minkowski coordinates and then each one is now evaluated at different mass. You can think about these as flavors of the system. Or you can think about this as your underlying parameters now depend on this dynamical variable, the mass. Either of these are completely consistent, and so Karsh has advocated this. I'm going to use these interchangeably because they really are the same thing. Okay, so now what I want to do is go back to my experimental data. The experimentalists tell us that the conductivity looks like this. It's the Drude form. So here's sigma 0, 1 over this part, which comes from the momentum relaxation. And let me just assume that these variables are continuous functions of the mass. So that my conductivity is just, the differential conductivity is just sigma dm. So let me just write the conductivity as a function of all of these parameters, which I'm now going to say are continuous functions of the mass. And I just have a simple integral to go and do. Are there any constraints on this integral which will preclude this funky omega to the minus 2/3 power law? And the answer to that is no. Okay, so I have a distribution for the density, which goes like this. I now have a charge which depends on the mass. So this is very different. This will be the anomalous dimension for the current. I now have a relaxation time which would also depend on the mass. This, in fact, will be related to the breaking of the diffeomorphism invariance in the system. Okay, I just go and perform the integral. And I set this equal to this. And the integral to do is this. And in fact, you end up with the correct answer. So with this choice, you can always choose these parameters such that you end up with the phase angle, 60 degrees, and omega to the 2/3. Okay, and that is exactly what they see experimentally. The phase angle is in fact 60 degrees. Well, it has to be 60 degrees if in fact you see omega to the 2/3. Causality will tell you that the real and the imaginary parts have to have the same phase relationship and have to have the same power law, and if they do, then the phase angle has to be 60 degrees. Okay, so we can explain the data. But all I've done is phenomenology. Okay? Okay, now I've introduced a bunch of parameters. This exponent here has to do with hyperscaling violation. So, sort of the difference between space and time and also essentially what I mean by length. This is the anomalous dimension. And this has to do with momentum loss. Okay, now the question I want to ask is an anomalous dimension necessary? You can in fact just set c equals to 1 and set this equal to 2/3, which means you can get all of this by setting b equal to 0. So I can certainly get my result for the omega to the minus 2/3 without any anomalous dimension. But there's something else that's going on. In the experiments, the Lorentz ratio is not equal to a constant. Now, the Lorentz ratio has to do with the difference between heat and essentially charge transport in the system. And for standard metals, this ratio is in fact equal to a constant. If in fact you're seeing something here that depends on temperature, that is directly related to the scaling dimension of the current, or at least any anomalous scaling of the current. Okay, so in fact, in my language, phi is directly related to b, and in fact, that will set phi equal to minus 2/3. Okay, so if you combine everything that we did with Hartnell and Karsh, what you find is, in fact, you need an anomalous dimension. So synthesis of all of our work with the experimental data requires that there be an anomalous dimension. Okay, which is a very sort of strange result, but it is what it is. Okay, now, let's go back and look at this sum over mass. Okay, what really is the sum over mass? Well, the sum over mass is just sum over energy. It means really what I'm doing, and mass is just 1 over length, so what I'm saying is that underneath the optical conductivity is a theory in which I need now to include an integral over all possible values of the energy to evaluate the optical conductivity at every value of the frequency, which means the stuff is inherently incoherent, which means there's an extra dimension which is hidden in the optical conductivity. Okay, which means that I need to actually go and do this sum from the UV all the way to the IR. Okay, so this representation of the continuous mass formalism of unparticles really represents an integral over a space-time which is actually bigger than just the actual Minkowski dimensions of the material. There's an extra dimension. Okay, now this construction doesn't include any gravity. Okay, now let's go back to my sum rule. The sum rule here tells us that in fact the actual number of charges is bigger. So the stuff coupling to the electromagnetic gauge is bigger than the number of things which have a particle content, because it's bigger than x, and x is the number of particles. So that's ultimately what you're trying to explain. So the question I want to ask is, what is the low energy model that gives you n effective bigger than x? And does such a theory include gravity? Okay, now this F sum rule is just tied to the kinetic energy. And it's just tied to the kinetic energy, in fact, being p squared over 2m. So it really just comes down to a commutator between p and x. And the reason it comes down to that is the current operator is just the momentum. And hence, you're bound to get this if, in fact, you have p squared over 2m. So if you don't have p squared over 2m, what do you end up with? Okay, so we just asked this question, what if you use a theory for the kinetic energy which goes as this derivative, but to some fractional power? Okay, and this fraction is just anything. Okay, what do you end up with? You can redo the sum rule, and this is what you end up with. Okay, so if alpha is less than 1, you're going to end up with W being bigger than N. So here's a plot of this. So I just redid the sum rule. Here's alpha equals 1, alpha less than 1, alpha bigger than 1. The experiments give you this. So we need alpha bigger than 1. Sorry, alpha less than 1. Okay, now, what theories have alpha less than 1? Okay, massive gravity. Okay, so a very nice paper came out recently that by Sophia and Greg that in fact argued that it's sort of an interesting connection, at least it's an interesting sort of construction in which only one of the directions has this sort of anomalous dimension, and if you integrate over that, then you end up with this theory. And the kinetic energy operator, in fact, for that has this operator delta phi, and in fact, actually this should be less than, it's not less than 0, it's actually a positive number, but it's less than, this number here is in fact of the right size to explain what we've done. Okay, now notice this. This is actually the theory on the boundary, and has derivatives with respect to the current that involve these fractional derivatives, at least with respect to the gauge field, which means there's an anomalous dimension of the current hidden in this theory. And this is the only kind of construction, as far as I can tell, that gives you this n effective bigger than x. Okay, so I would argue that all of this weird physics of the Cuprates, Montanus, is related to a theory that has momentum relaxation, F sum rule violation. Massive gravity seems to be a theory which has all of that. Okay, so here's sort of the bottom line. So the answer to my question, are the cuprates full of unparticles? I think the answer is yes. So there you have it.
For the unparticles to work, there is an ultraviolet cutoff, big M.
Right.
Where does big M come from?
Okay, it would be the bandwidth of the system, which in fact, so that would be sort of the upper bound for where the scaling regime happened. Okay.
So is this like an energy when the material blows apart, or?
Bandwidths are fairly large, but they aren't so large. In fact, in the cuprates, right, the scaling doesn't happen to all arbitrarily high energy scales.
Okay.
Okay? Okay. Yes, there's another.
So you're saying there's a critical regime.
Right.
Is there a transition? Or
I would argue that there is a transition. Remember now, this is
a function of what?
As a function of doping. Okay?
So somehow this is a zero temperature theory, except
Right.
that it might have been interrupted by superconductivity, but
Right.
This is a zero temperature theory.
Right.
And so it's a quantum critical point you're talking
Right.
about.
Absolutely. And I'm saying the excitations that are fundamentally arising at that quantum critical point are these things which have no particle content.
But you expect that to be the result of a sharp transition at zero temperature as a
Yeah.
function of doping.
Yes. So what I didn't say is that the onset of this is tied to a divergence in the self-energy. So it's the appearance of zeros of the single particle green function, which is a more technical thing, but that's ultimately how we stumbled onto this.
Is there any evidence experimentally that this scaling of the optical
conductivity.
third scaling or happens as a
Right. Oh yeah.
transition as a function of doping?
Yeah. It's not there. So the title of the paper was "The Onset of a Quantum Critical Point Near Optimal Doping." Okay. It's only happening.
Two-thirds paper.
The two-thirds paper. Right. It's really a narrow window near optimal doping, and hence it makes sense to argue that the stuff underlying it is something critical. Okay? Yes?
To clarify, these unparticles have variable mass, but do they have fixed energy? Yeah.
No, they don't. Mass is energy. So the whole thing I'm trying to explain is a metal that does not have quasi-particles. That does not have quasi-particles. So quasi-particles, I mean, if you look at photoemission on a metal, you put in a photoelectron and you see something come out, I mean, just come with light, a single photoelectron comes out. In the cuprates, as you saw, if you remove an electron, the spectrum rearranges on all energy scales. And if it rearranges on all energy scales, there can't be a particle description of what happened. So if there's anything, it's something at all energy scales. So what I've been struggling with the last 15 years is a theory of an incoherent metal. Okay, and so, no, the stuff exists it does not have a well-defined energy. That's the whole point. And that's why you're seeing this weird behavior for the current.
Is there any, can you even imagine why the particular structures that they Right, it's a rather specialized set of structures that you...
Right, okay, so yeah. So I would say that this all has to do with Mott physics. Okay, so...
In 2 dimensions or Mott physics?
I think it's Mott physics in general. Okay, yeah, I mean, I would say it's, I mean, of course, if there's a critical point, it's more severe in 2 dimensions, but I'd say it's just Mott physics in general. So anytime you have a state that is mediated by the interactions, you're going to see this sort of thing. So, I mean, I would say even nickel oxide would have to behave like this. But here's the thing. This is only happening if you can dope it. You can't dope nickel oxide. Okay, or look at all of the other traditional Mott insulators, which is why, I mean, Mott might have, introduced the Mott problem, but he didn't understand Mottness, because Mottness comes about from doping the system and realizing that there are these rearrangements of the spectrum that you can't predict from a single particle sort of picture. And that only happened with the Cuprates.
So in a section of talk, you derived a bunch of the scaling forms for the lens ratio and conductivity. You had
Yes.
You had
T to the minus phi over z.
Yeah, you had many copies, so you had essentially many...
Right, yes, that's right.
You had mass and parameters, etc.
Right.
I'm just wondering if I need that picture, and can I just recreate those formulas with some appropriate choice of the Green's function, some scaling form?
Okay, so the paper we wrote on this, what we did is we said, okay, let's play the game Phil was playing. And let's play this with the unparticle propagator. But let's do it properly. So let's gauge the unparticles with Wilson lines, and and since we have Wilson lines, we know exactly how the gauge appears in the action. Let's take 2 derivatives of log z to get out the conductivity, and don't make any mistakes, and you put in the vertex corrections. None of these power laws in the Green function survive. All you end up with is a conductivity which satisfies Ohm's law. You have L to the 2 minus D. And this should not come as a surprise. In a gauge invariant theory, you can't have any other power there. So regardless of what Green function you start with. So I don't know at this point how to do the following. I don't know how to start with a Green function, apply the Kubo formalism, and end up with these fractional power laws. I only know how to start with the Drude formula, do the phenomenology that I did, and end up with this. Now, a way around that might be this action that Sophia and Greg just came up with, in which you don't gauge the unparticles with Wilson lines, but with this very non-local type of Lagrangian that they wrote down. And so one of the things that I'm excited about is trying to calculate the conductivity from their action. And I don't know what's going to happen. But that's a very good question. We did that, so that long paper we wrote was exactly starting from this, redoing the Anderson calculation, and seeing you just end up with some prefactor that depends on the anomalous dimension times the conductivity of the free particle fields.
One more question before we break for drinks and snacks, Sophia?
So one of the things that Greg and I pointed out in the paper was that the rule of this massive gravity on ADS,
Yeah.
which is basically what you're describing,
Yeah.
you lose locality, so you lose an energy
Yes.
effect tensor, which is conserved.
Right.
Do you see that in your framework, or like do you have any explanation for
How momentum is...
What is the energy momentum tensor?
Right, okay, which is why I asked you, no, it cannot be conserved. It can't be, sorry, the energy is conserved, T00, but mu is not conserved. I mean, am I?
Okay, yeah, so.
But you're saying that even in your approach, T.
The point is that there's no energy momentum tensor when there's no locality, right?
Okay, okay, okay.
You see an emergence of non-locality, I guess.
Yes, okay, fine. I completely agree with that statement. But which is why if you were trying to figure out exactly what the mass, which is why you can't really tell me what your mass is in this non-local theory that you wrote down. And so, right. Yeah, so what I was trying to do is this. That exponent I introduced for the relaxation time, m going to a certain power, that can be related in sort of vanilla types of massive gravity theories to the radial dependence of the mass. And but in your approach, I don't know how to do that. Okay, so
Yeah, maybe they're
yeah.
So let's thank Philip one more time.